So I hope the screen is visible to you. Okay, the screen is visible to you. Someone can respond.
Yes, sir. Yes, sir.
Okay. So last week we were discussing equation of wind motion, and we have characterized different forces that actually governs the wind motion. So three real forces like pressure gradient force, gravitational force, and the frictional force. These are the three real forces which affects the wind, and due to the rotating frame of reference, or Earth is rotating, because of that there will be two apparent forces that we have seen, like centrifugal force and the Coriolis force. So using this all five forces, you can actually derive the acceleration term, and from that you can also derive the force term on a particular air parcel. Okay, and that will define its course of motion, like how the trajectory of the air will be governed by these three forces, effect of this sorry, not three, five forces. Now we have seen in detail pressure gradient force. So pressure gradient force that acts from when there is a high pressure and low pressure region. So the gradient will be always from high to low. And you can see that this is one of the force, the pressure gradient force, which actually initiate the motion of the air partial or air molecule. So because of this pressure gradient force, actually the wind starts to flow. And you can see that the other forces like the centrifugal force, the Coriolis force, those come into picture when there is some form of motion. Even the friction force, that comes into picture when there is some form of motion or the wind is already blowing. But what are the forces that helps to or initiate the wind wind motion? So the pressure gradient force, and in a vertical direction, due to the gravitational force also, the wind actually starts to move or accelerate. Okay, so these two are the primary force which initiate the wind motion. The others are the resulting force which acts due to the motion itself. Okay, so we have seen the mathematical formulation for the pressure gradient force, and in a three dimension, that is also you can see that this, which are pretty standard. And we also saw that the pressure gradient force on a horizontal scale actually creates some acceleration in the wind, whereas in the vertical direction it actually gives rise to the hydrostatic equation. This we have found from the order of magnitude analysis or scale analysis. Okay, and we have also seen the Coriolis force effect, like when there is motion of the wind and due to rotation of the earth, the air molecule or the wind itself will experience a Coriolis effect, and the magnitude of that is this one shown here, 2 omega sine phi v. So here v is the velocity of the wind or the relative velocity of the wind. So you can see that the Coriolis force is also a function of the wind velocity itself. Like if you have a larger wind speed, the Coriolis force will be higher. If you have a smaller wind speed, the Coriolis force will be lesser. Also, it depends on the latitude angle. Like it will be lesser, or it will be zero at the equator, because phi is zero at the equator, and as you go to the poles, it will be increasing. Okay, and the maximum it will happen at the pole. Okay, so this is already we have discussed, and we have performed the scale analysis, and from that we have simplified the equation, and we found only in the horizontal plane, like that is in xy plane, you get acceleration term in the wind, like du by dt and dv by dt, which are governed by your pressure gradient as well as your Coriolis force. Here you are basically neglecting the effect of centrifugal as well as the frictional force. Okay, so those we will incorporate gradually, like in subsequent slides. And this one is your the z direction or the vertical direction, where you saw that there is no acceleration term and is basically simplified to your hydrostatic equation. Okay, so here after you integrate it, basically you get P equals to rho g z. Okay, so which is your hydrostatic equation. So here F is your Coriolis parameter, we have already seen that 2 omega sine phi. So omega is your rate of rotation of your Earth. Okay, so then we have also seen the geostropic wind. In this case, basically your Coriolis force is balanced by your pressure gradient force, which normally occurs in the higher altitude or means above your atmospheric boundary layer. So in that region, you can see that the pressure gradient force can be balanced with your Coriolis force, and from that you can actually derive the geostropic wind velocity, like both in u and v or x and y direction. Okay. And this also you can write out in a general coordinate, like along a normal direction n, the Vg will be equals to, which is your geostropic wind. Excuse me. Excuse me. So 1 by rho f del p by del n. Okay. So here rho is your density of the air at that particular height, and f is your Coriolis parameter, and del p is your pressure gradient. So del p by del n is your pressure gradient along that normal direction. Okay. So yes, and we found that geostropic wind always blows along the or parallel to the isobars. So in this case, since we don't have the centrifugal force, so you see that the isobars are straight lines. Okay, and the direction of the geostropic wind, it is always parallel to the isobars. Okay, so these are the isobars of those lines where you have constant pressure. That I think this is you must be knowing. So these are high pressure. This is a high pressure isobar, and this is a low pressure isobar. And from the beginning, like at the earlier stage, since you have pressure gradient, wind starts to flow from high to low, but because of the effect of Coriolis force, it will starts to deviate from this direction, and it makes an angle. Then gradually we saw that this will continue to move until and unless this Coriolis force is balanced by your pressure gradient force, so which is shown here, and the wind will be flowing along this direction. Okay. So okay, so let's solve few numericals based on what we have discussed so far. So can you try out this, determine the Coriolis parameter for the latitude angle 20 degree, 40 degree and 60 degrees. Can you try out and let me know what are the values of Coriolis parameter you get?
Sir, can you show the equation once?
Correct. Yes, the Coriolis parameter equation is this one.
Sir, what value of omega shall we take? Excuse me, sir.
It is 1.3 into 10 to the power minus 4.
Sir, I am getting
4.97 10 power minus 5 for 20 degrees. Hello.
Yeah, can you tell? Okay, so here.
Yes, sir.
Okay, can you tell us how did you arrive at that solution? That's actually correct for 20 degrees.
So it is 2 omega sine this angle sine 20, and
Mm.
omega is
Omega
the
is?
yeah. So you can take 2 pi by 24 hours.
Yes. Okay. So here basically omega already is known to you, like Earth rotates on its own axis in once in a 24 hours, right? So 2 pi by omega, sorry, 2 pi by your time period is your 24 hours. In terms of second, you need to convert it, which you will get this much. Okay. Now, we of course you need to include in radians. So then once you substitute the values, you will get these numbers. Okay, so at 0 latitude angle, which is at equator, it is 0, and for these only the questions are 20, 40, and 60 are these values. 0.49 10 to the minus 4, and gradually it increases, as you can see. Okay, and it reaches to its maximum at the pole. So it's a pretty straightforward, but just the thing is you need to know omega. Okay, and substitute this value in radians. Okay, then let's go to the next one, which is again on the particular equation will be this one. Okay, well, you need to use this equation. So Vg is your gradient winds, sorry, geostopic wind speed, which is 1 by rho f del p by del n. Okay, please try to note down or take a snap. So rho is your density of air, f Coriolis parameter, and this is your gradient. Now, can you solve this? What is the geostopic wind speed for a pressure gradient of 200 Pascal per 100 kilometers when the density of air is this at a latitude angle of 20 degrees? Can you find out what is the geostopic wind speed?
Sir, can you show the question again?
Yes, sir. The density value.
So 33.5 meter per second.
Yeah, 33.5 kilometer होगा ना, kilometer per second लगी.
33.5, yes,
Oh, sorry,
33.5 meter per second. So basically the equation is very straightforward one, like the one we have derived. 1 by rho f del p by del n. So pressure gradient is known to you, which you convert it in terms of meter per Pascal per meter. F, I think just now we have derived, and Vg, then just substitute the values rho f del p by del n, you will get 33.5 meter per second. Okay, so that's correct. Okay, so this is the last one. Can you try out? One day recently, 100 kilometers per hour wind has observed to be blowing from west to east. Okay, at an altitude of 10 kilometers above Princeton. Okay, because I have taken this since the latitude of Princeton is 40 degrees. So what was the magnitude of the pressure gradient at 10 kilometers height? So you may find it helpful to note that Princeton is at a latitude of 40 degrees and density of the air at 10 kilometers is this much. So how do you derive the pressure gradient in this case? So the first thing you need to understand here is this wind speed is it a geostropic wind speed or the normal, like the wind what you see in the boundary layer? You can, since we haven't studied so far what is the height of the boundary layer, I give you a hint here. So this is actually a geostropic wind speed. All right. So for using the geostropic wind equation, you can solve this problem. So basically the same equation you need to use what you have used previously and find out the pressure gradient magnitude. Anyone could solve?
So 1.09 into 5.
Yeah. So something nearby 1.1 into 10 to the minus 3. So what you need to do, you just need to substitute the values. Rho is given here. F already we have derived in the question number 1. Vg is known to you, gradient wind speed 100 kilometers per hour. We convert it to meter per second. And height is immaterial. Basically the height is given here so that you can judge what is this wind actually, whether it is a geostropic wind or it's the wind which is nearer to the Earth's surface. Okay. So generally far away you go, there is the other defects do not come into picture, like the frictional force and centrifugal force. Of course, that will be very small when the wind is not blowing at a sufficiently larger speed, and the curvature also, it depends. Okay, so centrifugal force generally we neglect So that's why you can assume this to be a geostropic wind and solve using this equation. And this is what I got. I think someone else also got the same answer. Okay. Okay. So similarly, you can get or you can solve many other problems. So basically, this is to give you a brief idea about what kind of question you can expect. Okay. Now, okay, so like I have said, in general, we don't see your isobars to be straight lines, either horizontal or vertical lines. So the isobars are generally curved, okay, on the Earth's surface. So if you see any weather map, either in news channel or in when you browse for it, so you see that the isobars are curved, and that curvature is because of like there will be additional force which helps it to make this isobar curve. So basically that is your centrifugal force. Okay, so like we know that since Earth is rotating, so their partials will experience the centrifugal force also. Okay, so because of that, the isobars tends to be curved one. Okay. So there is one question which will come to our mind. Like I would like you to first solve about this or think about this first. What will be the resultant wind direction? Okay, let's say you have a low pressure region here and a high pressure region here, and the isobar is a circular one. Okay, and if there is this air partial here, on which direction it will move? Okay, on which direction it will move, whether it will move counterclockwise or clockwise. If it is in the northern hemisphere, and this is your low pressure region and this is your high pressure region, taking into account the pressure gradient force and your Coriolis force as well as your centrifugal force. So far we are not discussing about frictional force, so only we have discussed three forces. So can you just think like which direction this air parcel will move, whether in this way or this way, based on the force balance, of course. And this is, I am asking for the northern hemisphere. Any guess or any comment like how this air partial is going to move? If I have this setting low and high, that means at the center you have a low pressure and outside you have high pressure. There could be a reverse thing, like center you have high pressure and outside you have low pressure. Okay, so there could be two scenarios. So for this particular scenario, what do you think? The air will move this way or this way?
I think left means towards the left side.
Means
Because of the
counterclockwise or clockwise?
counterclockwise.
Will move along the counterclockwise. Yes, so actually that is correct answer, and that is valid for the northern hemisphere. Let me explain how it happens. Let's so you consider there are two scenarios. Let's focus for this one first. Low pressure and outside you have a high pressure. Okay, so like we know that pressure gradient force will act from higher to lower, which are shown in this red color lines. Okay, now your Coriolis force will act opposite to that. Okay, in the northern hemisphere it will act always will try to move the air partial towards its right. Okay, so because of that the air partial will starts to move towards its right in the northern hemisphere. Now there will be slightly imbalance between this pressure gradient force as well as the Coriolis force, and because of that the wind will try to be deflected, okay, towards its right, and that will be that extra deflection will be again balanced by your centrifugal force, which will act along this direction parallel to the Coriolis force direction. Okay, so because of this the wind will starts to rotate in counterclockwise direction when it is when the center has a low pressure, and the same logic you can apply and you can find out it will be on the clockwise direction for the when the center has a high pressure. Okay, so the detailed explanation I have written here, but I have explained already. If like is it clear to you? This is all because of the Coriolis force, how it acts in the northern hemisphere. Of course, this will be different in the southern hemisphere. It will be exactly opposite. All right. So generally what we say, or this is the nomenclature is followed, when the wind flows or blows in counterclockwise manner on a low pressure, it is called cyclonic flow. And the opposite one. Yes.
Can you please explain once again? I couldn't get the
Okay,
word.
so here you can see that on this low pressure, let's see here, on this low pressure region, you get actually the first force you will get is your high pressure gradient force. So because outside you have high pressure and you have low pressure here, so the pressure gradient force will be directed from out to in. Okay, so this will be your direction of the pressure gradient force. Let's focus on this one. And the Coriolis force that will act along this direction, perpendicular to this, along this direction, because it is in the northern hemisphere. It will be in the opposite direction if it is in the southern hemisphere. Okay, so now you can see that between Coriolis force these perpendicular two, it will be perpendicular to the relative wind. At that moment, whatever wind is initiating, right? Let's say the air molecule is starting from here. It is going like this. Okay, the Coriolis force will be perpendicular to that wind, the relative velocity at that particular instance. Okay, so now it is perpendicular to that. So you can see that between these two, the resultant force will be deflecting the wind towards its right. Okay, deflecting towards its right, and that particular deflection will be further balanced by the centrifugal force. Since it is in the rotating frame of reference, so that will be again balanced by the centrifugal force, and it will achieve a steady rotation. Okay, so basically due to that centrifugal force, the rotation will be steady. So then there will be all these three forces will be balancing, and it will give you a steady state condition. Is it clear now?
Sorry, sir, I couldn't.
I think you draw the force vector diagram, it will be more clearer, and the explanation I have written here. If you still face difficulty, just let me know. Okay. The same thing will be also applicable for the high pressure. When you have a center at high pressure and outside you have low pressure, it will be exactly in the opposite way. So because you know that the pressure gradient will act in this direction, and your Coriolis force will act perpendicular to it, and the northern hemisphere it will along this way, and because of the force balance it will create this clockwise sense. So this clockwise rotation in the northern hemisphere, it is called anticyclonic flow, and in the anti-clockwise flow in the northern hemisphere, it is called cyclonic flow. Okay, so that you need to remember. This is the nomenclature. It is generally followed in the northern hemisphere, and exactly opposite is followed in the southern hemisphere. Okay, so we will be focusing mostly on the northern hemisphere itself. We will not go to the southern hemisphere. All right. Okay, so now you can see that depending on based on the pressure at the center of the circulation, it can be low or high. So your centrifugal force, it will be either parallel to the pressure gradient force or opposite to the pressure gradient force, or in the same sense you can say that it will be either parallel to your Coriolis force or opposite to the Coriolis force. Okay, so we take centrifugal force as negative if it is opposite to the pressure gradient force, and we take centrifugal force to be positive if it is parallel to the pressure gradient force. So based on the pressure gradient, how whether it is parallel to the pressure gradient force, we say centrifugal force is positive or negative. This is the sign convention we follow. That is what I have shown here. What is the sign convention? So from the pressure gradient and centrifugal force, you can actually, if they are in the same direction, you take positive. If they are in the opposite direction, you take negative. Okay, and similar to your geostropic wind, there could be another scenario where these three forces, your centrifugal force, Coriolis force, and the pressure gradient force, they balance with each other. Okay, so that particular situation may arise, and so basically in a mathematical form you can write it in this way: your Coriolis force is balanced with your pressure gradient force and your centrifugal force, and like I have said, it can be plus or minus depending on whether it is along the direction of the pressure gradient or opposite to it. Okay, so you can achieve a force balance from it. Okay, now we know all these terms already. Okay, so your Coriolis force term we already know, 2 omega v sine phi. Okay, then the other one is the pressure gradient force, also we know along any normal direction, this will be del p by dp by dl, and you get rho of air at that particular height, and this is your, actually this is the force, your centrifugal force. Okay, this is also, you know, v square by r, where your r is your actually from your center of the circulation, the distance of the isobar. Okay, so I'll be using either small r or the capital R. So I have another equation where I have capital R in the later on. So both r and small r and capital R, that represents the radius of the curvature. Okay, so this equation is basically the force balance between your pressure gradient, centrifugal, and the Coriolis force. Any question?
Sir, shouldn't the means the centrifugal force be out of the plane and the pressure gradient in the plane? How can you balance the direction?
How can you
Means how can
balance?
means
It depends on the curvature, right? Whether it is rotating in a clock, like whether you have a high pressure here or a low pressure here. Based on that, your pressure gradient force will be derived, whether it is going, pointing outward or pointing inward. And your centrifugal force will be always, it will be outside, right? Towards the outer side. This is normally your force vector.
Right. It's in the plane of the paper, right?
In the plane of the paper.
But shouldn't it be outside
we are considering this in one particular plane, XY plane. This is in the horizontal plane. We are not considering the vertical plane. These all three forces are maintained in one particular plane, not in a 3D space.
Okay, sir.
Okay. So you get this equation. Now you can see that there will be two different possibilities. Okay, like if you want to solve for the gradient wind, like the gradient wind, which what I said is it's a balance between these three forces. Okay, so from this equation, if you want to derive what is the actually the speed of this gradient wind from this quadratic equation, you can actually solve for it. Okay, and you can get either this or this equation based on whether you are doing a cyclonic wind or an anticyclonic. That means plus or minus. Okay, so these will be your resulting equation. I did not show the detailed derivation here, but you can very well come from here to here. Both this equation can be derived by just choosing the appropriate sign, cyclonic wind and anticyclonic wind.
So,
now,
in
yes.
the equation, wouldn't it be like pressure gradient force will be in the like negative sign, right?
Pressure gradient force will be negative sign. Okay, yes, there should be a negative sign, but again it will be when you simplify that, I think the final form of the equation will be this. If yes, so I think I missed a negative sign here. All right. So when you simplify, you will get this is your cyclonic wind and this will be your anticyclonic wind. Okay. Now, okay, so my point here is what will be your what do you call the sign of this radical? Since you have a square root here, it can take both positive and negative, right? So So the sign is actually determined based on this particular value. Like if you don't have any pressure gradient at a particular location, your gradient wind should go to 0. Right? When there is no pressure gradient, there should not be any wind flowing, right? So from that, you can actually derive what will be the sign of this radical. Okay, so for example, in this case, let's consider the cyclonic flow. So I make it 0. Okay, if I make it 0, then to get 0 VGR, I must get positive value of this. Okay, all right. So if you come to the second equation, still if I have dp by dn equals to 0, then of course for this case also I need to get the positive value. So you get one correct solution, the other one is your incorrect solution. That is what actually I want to highlight here. So which solution you need to take? The positive solution you need to take, because you need to satisfy that your dp by dn should be, when it goes to 0, your VGR should be 0. Okay, your gradient wind speed should go to 0, because without any pressure gradient you should not get any wind speed. Now there is another limitation you can also see here. For this particular equation, cyclonic equation, this term under the square root will always be positive value. Okay, del p by del n, there is no negative term here, whereas you see here there is a negative sign here. So what it means? It means that there is up to certain parameter space, like either r or dp by dn, you can only get this wind. Otherwise, it will give you a complex solution, or which is non-real or non-existing solution. All right. So that is the limit here. So for cyclonic wind, it can go to any speed. Okay. Whereas for anticyclonic wind, you have a limitation, speed limitation, and the maximum wind speed that you can get is when this particular term goes to 0, because you have a negative sign here. So the maximum wind speed is this much. Okay, is it clear? And based on that maximum wind speed, you can actually see how much will be your radius of curvature. Now someone may argue like I can very well increase this speed and I can also keep on increase this, so I can go for a higher this particular value, because you can see that this value here, the Coriolis force term, is also here in the outside of your radical. So you have a scope to increase this simultaneously. You have a scope to increase this, but that is not feasible, because in general you saw that the Coriolis parameter is very small, like of the order of 10 to the minus 5 or so. And if you go for a higher radius, the other alternative is you go for a very large radius, which is not even feasible. Okay, you cannot go like of that long radius where you can still exist the pressure gradient. Means you still have the pressure gradient in that large scale, which is not feasible. So generally this particular anticyclonic wind, they exist in a very small length scale, or it can be simply neglected. Okay, so that is what I want to highlight here. The cyclonic wind, it can go to any radius. Sometimes you see that whatever in the news you see when there is a hurricane or storm, you basically see this cyclonic wind, which can have hundreds of kilometers, sometimes like thousands of kilometers also. It's spread across, and it evolves over time for more than days, sometimes months also it evolves. Okay, but anticyclonic wind doesn't exist for that long. Okay, any question? Okay, if no, okay, if no question, then I will stop here because I need to go for the other meeting. So we will see. So we'll meet again tomorrow morning at 8 o'clock. Okay. So till then, bye bye. If you have any question, I can take for 1 or 2 minutes. If not, then we end here.
Sir, are you going to upload these notes?
Notes, yes. Like I have mentioned earlier, once this chapter is over, which I think may not be possible, and I don't know whether it is possible to complete tomorrow itself, or it may go to Monday. Okay, maximum Monday we will. Sorry, Monday. I'm telling next Wednesday, Monday, because last semester I used to have class on Monday, so I'm still confused. Okay, so it will be either tomorrow I will finish it up, or on after Wednesday's class I will upload. Then I will give you sufficient time. Then we will also have a test on this particular chapter. We will discuss about that when we can schedule a test on this particular chapter. Okay.
Sir, I had a question that just now that you said that that cyclonic wind remains for longer time. I couldn't get that one.
Okay, so why it can be for longer time? Like you can see that here in this equation there is no parameter which is restricting it to not to grow. Okay, like whatever
Yes.
pressure gradient you can have, like you can have any amount of pressure gradient. Okay, and this pressure gradient can be generated by different parameters. So we are not discussing what causes this pressure gradient, like thermal effects can be there. There can be like we saw, I think already we have discussed, there are solar radiation, terrestrial radiation, because of which the thermal distribution changes, and due to that you can get this pressure gradient, any number of pressure gradient. And if certain pressure gradient is helping you to generate cyclonic wind, it may sustain it. Okay, there is no parameter which is telling that the cyclonic wind will not grow. But whereas in this case, you see that there is the opposite effect. Okay, you can see that the Coriolis force and the pressure gradient force, they act in an opposite manner. Okay, so that's why it cannot sustain beyond a certain pressure gradient. Okay, so that's the thing.
Thank you.
Okay then, so I have already taken the attendance. Okay, see you guys tomorrow. Bye bye.
Thank you, sir.
Thank you, sir.